All right, guys, good morning. Hope you're having a great day. We are going to take a look at density today. We are going to get started off with a little brain teaser to get our minds warmed up before we delve into the depths of density. All right, so which do we think weighs more, 1 pound of feathers or 1 pound of bricks? Think about your answer. All right, do we got it? All right, here's the answer. Da-da-da! It turns out they weigh the same. Each has a weight of 1 pound, so that's telling us we have the same amount of both. I know, pretty crazy. If you got that wrong, you may have been thinking about the density. Okay. Because of density, we would need a lot more feathers than bricks to get our 1 pound. Okay. But if we have 1 pound of both, we have the same amount of each. We're going to have the same weight. However, yes, we are going to need a lot more feathers to equal that same weight as our bricks. So, what exactly is density? So, density is going to take both mass and volume into account. It is going to tell us how tightly packed the particles of a substance are. So, when we look at density, when we calculate it, we're going to say that our density is equal to the mass of a substance divided by its volume. Okay, so again, density takes into account both mass and volume. A fun way to remember this is that if you forget it, you are going to break my heart. Okay, you're going to break your teacher's heart if you forget the formula for density. Okay, and we can see that it's still mass over volume. Okay. Since we have mass divided by volume, when we calculate density, we are going to get units of either grams per milliliter or grams per centimeter cubed. Okay, so remember that fun little fact that 1 milliliter and 1 centimeter cubed are both units of volume, and it just turns out that they're the same amount. Okay? So we can use either unit for density. When I was saying those, you should have heard a key word there. Grams per milliliters, grams per centimeter cubed. Since we have that word per in there, that tells us that we can use density as a conversion factor. It's all coming together now. Okay, so density is going to tell us how tightly packed our particles are. What mass do we have per unit of volume? How many particles do we have per milliliter or per centimeter cubed? Okay, so density is going to be an intensive property. So that means it does not depend on how much of a substance you have. Whether we have a gold coin or a big gold bar, either way, our density of each is going to be 19.3 grams per centimeter cubed. So it doesn't matter how much you have, the density is always going to be the same. We can link this back to our states of matter that we looked at in chapter 1. Tightly. Okay, that means for per unit. So much a great deal amount of particles. So that means we're going to have a high density. Whereas when we look at our liquid, these guys are not as tightly packed. They're a little bit more spread out. So they are going to have a little bit lower density than our solid. Liquids, they're always in the middle. Whereas our gas, if we look at our gases now, we can see those gas particles are more spread out. So we have less particles per unit of volume, which means we're going to have the lowest density with our gases. Our gases are loosely packed, so these guys are going to have the lowest density. Okay. If we look at some examples here, if we look at lead, okay, lead is going to have a density of about 11.4 grams per centimeter cubed. Okay. Whereas if we look at water or liquid, that density is going to be lower. For water, our densities are going to be about 1 gram per milliliter. And then our gases are going to be even smaller. Our gases have such a small density that CO2's density is about 0.00198 grams per milliliter. So we can see that our gas particles are substantially more spread out than our solid particles. They're solid, they're the most compact, so they are going to have the highest density. We're doing calculations with density. So in this example, we have my favorite candy, M&Ms. We have 30 centimeters cubed worth of M&Ms. If the mass of these M&Ms is 2,580 centigrams, what is the density of an M&M? All right, so here we are looking for the density. So remember, our equation for density is equal to mass divided by volume. Okay? And since we're doing mass divided by volume, when we do that, we should get units of grams per milliliter or grams per centimeter cubed. So if I go back and look at my problem, it tells us that I have 30 centimeters cubed of M&Ms. This is going to be my volume. My hint there is that we see this cubed. Remember, cubed units are going to tell us our volume. Okay. If I go on to read, it says the mass of my M&Ms is 2,580 centigrams. And again, that grams there is another hint that this is going to be my mass. Okay, so I know my mass and I know my volume. But before I can plug this into my equation, I need to convert my centigrams to grams because density is grams per centimeter cubed. So I'll take my 2,580 centigrams, and I know that there's 100 centigrams for every 1 gram. So I divide by 100, and I have 25.8 grams of M&Ms. What a dream. Love M&Ms. All right. Now that we are here, now we are able to plug it into our density formula. So I know my density is my mass, my 25.8, divided by my volume. So divided by that 30 centimeter cubed. And I plug that in my calculator, I should get 0.86 grams per centimeter cubed. Okay. We just need to also make sure that our sig figs are correct. If I look at my two measurements, my 30 is going to have only 2 sig figs, whereas my 25.8 is going to have 3. So that means my final answer should also have 2 sig figs. And when I go over to look at it, I only have 2, so I am good to go. Okay. So what this actually tells us is that for every 1 centimeter cubed of M&Ms that we have 0.86 grams. Okay. So for every 1 centimeter cubed or unit of volume, we have 0.86 grams. Okay. So let's say we had 10 centimeters cubed of M&Ms. And we want to figure out what mass that would have. If I know for every 1 centimeter cubed we have 0.86 grams, I can use that as a conversion factor. So for every 1 centimeter cubed, I have 0.86 grams. So that means if I have 10 centimeters cubed, I would have a mass of 8.6 grams of M&Ms. So that density tells me how many particles I should have per unit of volume. Challenging. So in this example, we have oxygen with a density of 0.01429, and milk has a density of 1.033 grams per milliliter. We want to see how many milliliters of oxygen we would need to have the same mass of 3 milliliters of milk. Okay, so we have a lot going on in this one. So I'm going to separate my data into what I know about my oxygen and what I know about my milk. Okay, so this tells me that oxygen has a density of 0.001429 grams per milliliter. And my milk is going to have a density of 1.33 grams per milliliter. So I know my density of each of my substances. I can see that my milk has a higher density, so that's going to tell me that my milk particles are more closely packed than my oxygen particles. So our end goal is to figure out how many milliliters of oxygen. So we want to find out what volume of oxygen do we need to have the same mass as 3 milliliters of milk. So if we look at this, it tells me my volume of my milk at 3.00 milliliters. So my end goal is to find out what volume of oxygen we would need to have the same mass as 3 milliliters of milk. Okay, so when you have problems like this, when you're working with two different things, we want to start off by thinking, which substance do we know more about? Do we know more about our oxygen or more about our milk? And we can see here that we know more about our milk, so we're going to start there. Okay, start with whichever one you know more information about. Okay, so these are all about density. We know density is equal to mass divided by volume. So if I look at my milk, I know my density and I know my volume. So I should be able to find what mass of milk I have. I can do this one of two ways. My first option is I can just plug these values into the density equation. So my density, oh here, we'll switch this down a little bit. So my density of milk, 1.033, is equal to my mass divided by my volume. I can just multiply each side by my volume by the 3.00, and we should find that our mass here is 3.099 grams. So that's one way we can do it. Just plug those values in for our density equation. Our second way we can do it is to use density as a conversion factor. Okay, we know we have 3 milliliters, and that for every 1 milliliter, we have 1.033 grams. That means we would do 3 times 1.033 for a total of 3.099 grams. So either way you want to solve it works. It's completely up to you. Okay, so now we know what mass of milk we have. Real quick, just looking at our sig figs here, when we're multiplying and dividing, we want to have the same number of sig figs as the number with the least amount. So there's 1, 2, 3 in our volume, and 1, 2, 3, 4 in our density. 3 is less, so that means we would want our final answer to only have 3. So 1, 2, 3. Okay. We are going to keep all digits for now, though, just so we don't have rounding errors, but I'm just going to mark which ones are significant. Okay, so now we can add this piece of information about our milk. We know our mass is 3.099 grams. My goal is to find what volume of oxygen I would need to have the same mass. So that means that if my mass of milk is 3.099, my mass of oxygen would also have to be 3.099 grams. Okay, because our goal there again is to have the same mass. Now when I look at my oxygen, okay, again, we're using the density equation. I know my density and I know my mass. I know 2 out of the 3 things, so I can solve for my volume. And so what volume of oxygen would correspond with 3.099 grams? So again, we can solve this 2 ways. First way, we can just plug it into our equation. We can set our density equal to our mass divided by our volume. Okay. If you do this, just be careful because that V, that volume, what we're trying to solve for is in the denominator. So the first thing we're going to want to do is multiply each side by V to move that up top. So we'd have 0.001429 V is equal to 3.099. Now we can see to get V by itself, I would need to divide both sides by the density. And I would then find that my volume here is 2,168.6 milliliters. Again, when we're looking at density, our volume is always milliliters or centimeters cubed. Okay. If we wanted to, we could have also used density as a conversion factor. Because I know if I have 3.099 grams for every 1 milliliter of oxygen that I have 0.001429 grams. And that would tell me that I would have 2,168.6 milliliters. Again, either way you want to solve it is totally fine. It's just whatever makes sense to you. However, before I block that in, we need to take a look at our sig figs. So I said this 3.099 only had 3 sig figs based on our calculations over here. That means our final answer can also only have 1, 2, 3 sig figs. So the 6 is going to be my last sig fig. I have to look to what's next to it, and it's an 8, which will round that 6 up. So I have 2,170 milliliters of oxygen. Okay, so for these guys, when you have multiple things going on, break it up. What do you know about each of the substances? Categorize it. Then look to see which substance do you know more about, and start off by looking at them. Look to see what variable you can solve for. Do you know, are you trying to solve for your volume or for your mass? And then for this one, since they had the same mass, whatever mass we had of milk, we knew we had to have that same mass for our oxygen. And then we could, again, use that density equation or use density as a conversion factor to figure out what volume of oxygen corresponded with a mass of 3.09 grams. Okay. So please let me know if you guys have any questions. Otherwise, have a great day.